Hi, my name's Alex, and today I'm going to be talking about IA-CCF, individual accountability for permission ledgers. In commercial environments, permission ledgers are the most promising platform for building trustworthy distributed systems. However, they can only tolerate a limited number of replicas failing, and this brings their trustworthiness into question. So what is a permission ledger? A permission ledger is a distributed system that provides a service for its users, for example, a banking application, and records events in the ledger. They are made up by multiple people coming together to form a consortium, and each consortium member brings some replicas, and the replicas are operated by their members. Within any deployment, only authorized users, members, and replicas can access the system. Permission ledgers often use Byzantine fault-tolerant consensus protocols, which provide safety and liveness if less than a third of the replicas misbehave. In addition, a ledger created by a Byzantine consensus protocol will be correct if less than a third of the replicas misbehave, could emit transactions if a third or more of the replicas misbehave, or could be completely rewritten if 2/3 or more of the replicas misbehave. Auditing the ledger allows us to detect if a problem or misbehavior occurred, but this is not enough. When problems are detected, all the members are blamed for the misbehavior, as we have no way of knowing which specific replicas are at fault. This is known as group accountability. We want to know which specific replicas misbehaved to make sure that the members operating them can be held accountable. We want individual accountability. Individual accountability is the idea that a member is responsible for the replicas that they are operating. This incentivizes members to ensure that the replicators are running correctly, that they themselves do not perform any malicious actions, and that they protect the replica against any outside attackers. Similar techniques are used in regulated industries such as finance. Within the context of a permission ledger, for auditing to introduce a deterrence, we must be able to find precisely which replica is at fault. Would it not be great if we could build a trustworthy permission ledger which can guarantee safety and liveness when a small number of replicas misbehave, or guarantee a consequence when a large number of replicas misbehave? To build this, we need to co-design the Byzantine Consensus Protocol, ledger, receipts, and governance. We built individually accountable CCF, or IA-CCF. By co-designing these features, IA-CCF replicas are only required to sign one protocol message in a batch and reuse the same signature in receipts and the ledger. In addition, IA-CCF reduces latency by responding to client requests in 2 network round trips. To understand how IA-CCF and its Byzantine Consensus Protocol work, let us consider the case of Alice. Alice needs to set up a complex banking transaction to deposit her salary. She deposits part of her salary into Bob's account, but only after paying bills and taxes. Alice's bank is part of a consortium which utilizes IA-CCF, and IA-CCF implements L-PBFT as its consensus protocol. L-PBFT designates a primary replica and a number of backup replicas. To start her transaction, Alice sends her request to all the replicas. Then Bank Green, the acting primary, decides to order her request. However, unlike PBFT, the primary replica will execute the requests and then create a pre-prepare message, which includes a hash of the execution. Green Bank then records a pre-prepare message and the executed requests onto its ledger to ensure it has proof that the request executed. Finally, the Green Bank will send the pre-prepare message to the yellow, blue, and orange banks. When the yellow and blue banks receive the pre-prepare message, they execute the order requests and ensure they produce the same execution as the Green Bank. This early execution ensures that once a request is committed by a quorum of replicas, there is agreement on the execution. After the replicas finish executing the requests, they write the pre-prepare message and the executed request to their ledger. Next, the 2 banks create their own prepare messages, which state that they agree with the primary replica's execution and ordering, and send this pre-prepare message to all the other replicas. Once a replica has received a pre-prepare message and a quorum of prepare messages, it creates a commit and reply message. The reply messages are sent to the client, which converts the replies into a universally verifiable receipt, tying the replica's execution to the request and the reply. In parallel to sending the reply messages, replicas send their commit messages to one another. Once a replica has received a quorum of commit messages, the replica considers the batch committed and is ready to start working on the next batch. In the execution we just saw, all the replicas behave correctly. But what if three of the four replicas are controlled by malicious actors? Let's go back to our example of Alice and Bob, when 3 of the 4 replicas are run by malicious actors. Alice wants to deposit $1 million into Bob's account. She creates a deposit request, sends it to IA-CCF, which records it to the ledger and gives her back a receipt. She provides a receipt to Bob to show that her deposit executed correctly, and then Bob decides to withdraw the funds. Bob creates a withdrawal transaction, sends it to IA-CCF, and receives a receipt. However, his receipt says that he has insufficient funds. Bob is suspicious because he knows he did not make any other withdrawals and decides to perform an audit. To perform the audit, Bob obtains a copy of the ledger and checkpoint from one of the replicas. Bob loads the checkpoint, then he will execute several transactions from the ledger. Next, he re-executes Alice's deposit transaction and matches it to her receipt. Then he executes some more transactions from the ledger, re-executes his withdrawal transaction, and matches to a receipt. Bob discovers that the replicas incorrectly executed his withdrawal transaction. With group accountability, all the replicas and their members would be blamed. However, Bob is using IA-CCF, and he knows that the receipt is made up from replies from 3 of the replicas. He can match replies to the replicas, give this to an enforcement authority that can blame the members that run the replicas. Now, let's consider a more complex attack. What if the ledger is completely rewritten and the checkpoints are updated to reflect the new state? IA-CCF can still address this problem. When we reuse our previous example, Bob will load a checkpoint and look at the checkpoint hash and compare the checkpoint hash to the hash inside of Alice's receipt and see that these two do not match. In fact, none of the replicas can produce a checkpoint hash that would match the hash in Alice's receipt. With group accountability, again, all the replicas would have to be blamed, but with individual accountability and IA-CCF, the enforcement authority can only blame the members that run the replicas that misbehaved. In the previous 2 auditing examples, the current set of replicas and members did not change. But what if they did? IA-CCF allows replicas and members to change through the governance. Members create proposals to add or remove a member or a replica, and other members vote on the proposal. If a proposal is accepted, the reconfiguration protocol will perform the change, and we record all reconfigurations along with their proposals and votes in a governance subledger. So how do clients know which replicas can sign their receipts? Each receipt contains a hash of the last reconfiguration from the governance subledger. The client uses this hash to obtain the governance subledger from a replica, then looks through the entire hash starting from the Genesis transaction going all the way to the current replica set. We show how auditing works with a reconfiguration in our paper and provide a proof. Now, let's look at IA-CCF's implementation and performance. We built IA-CCF on top of Microsoft's Confidential Consortium framework. CCF uses trusted hardware to harden replicas. It executes transactions against a key value store and records state mutations on a ledger and in receipts, allowing users to audit the service through a combination of receipts and the ledger itself. IA-CCF takes many of these features and co-designs the Byzantine Consensus Protocol, ledger, receipts, and governance protocol to add individual accountability. We evaluated IA-CCF in both a LAN and a WAN environment using the small bank benchmark, a benchmark that mimics the operations of a small bank where clients transfer funds between one another. Our LAN environment was in our data center with an isolated network, while the WAN environment was across 3 geo-distributed Azure data centers. In our LAN environment, we look at the throughput and latency of IA-CCF. On the x-axis, we show the number of transactions executed per second, and the y-axis is the average latency of each transaction. In all our experiments, we show a gradually increasing number of transactions sent by an increasing number of clients that are run on remote nodes. Here, we can see that IA-CCF obtains a peak throughput of over 47,000 transactions per second. For comparison, we looked at peer review, a general-purpose technique for ensuring accountability in distributed systems. IA-CCF, using the peer review method for accountability, has peak throughput 2 orders of magnitude lower. From this, we can see that co-designing the Byzantine Consensus Protocol, ledger, receipts, and governance greatly improves performance of individually accountable permission ledgers. We use our WAN environment to understand how well IA-CCF scales. In this graph, the x-axis shows the number of replicas, and the y-axis is the number of executed transactions per second. Here, we observe the throughput when we increase the replica count, going from 4 transactions that execute approximately 40,000 transactions per second to 64 replicas that execute approximately 15,000 transactions per second. For comparison, IA-CCF, using the peer review method of accountability, has throughput 2 orders of magnitude lower. Since replicas need to be controlled by independent entities, we believe that consortiums with 64 replicas to be rare, and the majority of them will be much smaller. Next, we look at the performance and impact of adding features to a Byzantine Consensus Protocol so that it becomes an individually accountable permission ledger. To start, we look at hot stuff, a well-known Byzantine Consensus Protocol. L-PBFT, IA-CCF's consensus protocol, has approximately the same performance. When we introduce IA-CCF's transaction engine and key value store, we can see that throughput more than halves, while signing the consensus protocol messages reduces throughput approximately 10%. And signing request messages sent by the clients, which then must be verified by the replicas themselves, more than halves performance. Next, we introduce sending receipts from the replicas to the clients that send requests. This has a minimal impact on performance and brings us to full IA-CCF. From here, we can see that the consensus protocol is not the bottleneck when building individually accountable permission ledgers. In conclusion, we built IA-CCF, a permission ledger which provides individual accountability to ensure members which run malicious replicas that compromise the safety of the permission ledger are always held individually accountable. We did this by co-designing the Byzantine Consensus Protocol, ledger, receipts, and governance. We obtain high throughput by only requiring replicas to sign 1 protocol message in a batch, and low latency by returning receipts in 2 network round trips. And in our paper, we showed that individual accountability can always be obtained if the Byzantine Consensus Protocol is compromised. Thank you.